All right, so today is sort of exciting because we have our very own Kim Leine, who's, in addition to organizing colloquiums, does really cool research. So he's been a researcher here, I think, almost 10 years, yeah?
Yeah.
And he's worked in a bunch of different areas. He is really well known for work in fully homomorphic encryption. He's also done cool stuff with us in end-to-end encryption and key transparency. And today he's going to talk about a different project, which is he's also been working on for several years on looking at accountability and some incentives, some privacy, things like that.
Awesome. Thanks, Melissa. So as you can see, the talk title is Sandi, Assistant for Accountability. Whatever that means will become hopefully clear during the talk. This is joint work with our colleagues Betul and Radames, who are here, as well as our former intern Simon Langowski. The paper will be actually presented at the Euro S&P this year. Okay, the motivation for this project came from this question. With LLMs, how can we trust digital communication? With LLMs, of course, we all know very well that it's super easy to create a lot of stuff. And if you receive this kind of communication, like some automated emails or some messages, maybe phone calls, text messages, how can you know to trust that? And similarly, how can others know that they can trust communication that they get from you? The communication can happen really on different platforms, like email, SMS, or direct messages on anything like social media platforms or such. Of course, part of this question is really trivial. If I already know who I'm getting my messages from, there's really nothing there. I already might have some opinion about that person, and I can make an educated guess. Should I trust whatever they say? Maybe it's highly likely that they're not trying to scam me, for example. So this case is not that interesting to us. Now, but what if I don't know that person? So I get some message from someone. They claim they are a recruiter, or they claim they are a salesperson, or they are a long-lost relative. Then what? Well, certainly I could trust or not trust by default. I could be someone who just trusts everything, or I could be someone who never picks up their phone when it's an unknown number. Or I could have some sort of heuristic that I use to determine whether I trust or not. I could also ask others about their experiences with this sender of the message. So the problem is, though, that what if it's just some, let's say a salesperson. That's a great example here. So I'm contacted by someone who's trying to sell something to me for whatever reason. Like how would I know who to ask? Like how would it be likely that someone else who I know and trust has interacted with the same person? Well, there's a third option, which is what we explore in this work. And that is, I could trust based on some sort of reputation concept. Now, of course, but there's a lot to clarify here. I mean, in fact, you can easily imagine that, well, I could have some sort of reputation system for people. I might want to have a reputation where, like, this person has a really great reputation, and others who have good experiences with them can, like, thumbs up or thumbs down them. Or this person has bad reputation, they get a lot of thumbs down, and so on. And there's a lot of problems with this kind of naive idea. First of all, I want to take kind of a step back here and be really concise and clear about what is it that we're trying to solve here. All we care about is whether I can trust whoever is sending me that message, or whatever is sending me that message. It doesn't have to be a person. We don't actually need to solve the identity problem. I don't need to know that it's like Betul. I don't need to know that it's a particular machine that's sending it to me. I don't really care. All I care is whether I can trust them. So it's very important to make sure that we're not overcomplicating the problem by starting to talk about like proof of humanity or things like this. I mean, famously, the identity problem isn't solved really for the world or for the internet. We certainly don't want to learn any unnecessary identifying information. So you could imagine concepts like, let's digitally sign all emails. But again, like, is that really necessary? No, because these things are identifying. Now you need to have some sort of key directory. Again, is this really what we would want? Does the reputation system that we would maybe have really require this? And the answer is no. Next, another difficulty that we need to consider here is that reputation systems, when you just naively think of it, well, they are used a lot, like everywhere. You probably use reputation systems every day when you use the internet, but they are vulnerable to all kinds of threats. And it's just that often these threats are not really on a super critical path for your experience, that you don't really need to care about it so much. But if we think of this kind of reputation system for communication, I mean, how would I know that a group of friends doesn't just come together and upvote each other, and now everyone has a fantastic reputation, right? Another problem is that, well, what if I get a message from someone, and I'm like, wow, this is a real, really unpleasant message, totally inappropriate. I'm just gonna report them thumbs down times 10, and they might find out. And they might retaliate. What if it's my manager? Well, hopefully that wouldn't happen, but it might, right? So there's really very real concerns about retaliation. Somehow this needs to be prevented. And finally, as someone who is, let's say, a reputation owner, if I'm the subject of the reputation, then I would certainly want to know that the system works correctly and somehow my reputation is not being skewed or manipulated in some bad way. Another really interesting and important difficulty I want to raise is that it's often really unclear what kind of behavior reputation systems incentivize, or what kind of behavior do they drive you towards. So actually a very good example is GitHub stars. I really love this example because it's like the absolute simplest reputation system in some sense. You just star a project and there's nothing else you can do, right? It's like a unary system. But even there, it's not clear what kind of behavior it drives the reputation subject towards. So if I have a repository, well, first of all, like, why do I want stars? Does that do something good to me? And even if I want stars, what's the best way of getting the stars? Does that mean that I should make a very good repository, have very good quality code, less bugs? Or does it mean that I should just go on Reddit and advertise my repo? It's not really clear what kind of behavior it drives towards. And the same questions you can ask about all other reputation systems that are used. It's just that in practice, this doesn't really come up as a problem to normal users of this system. But if we talk about, again, reputation for people, where all of you might be the reputation subjects, then it's a little bit of a different question. And finally, it's very important to, well, therefore, like, it's very important to somehow explain and justify why the reputation system that we have actually drives for good behavior. Because, well, if the reputation system doesn't drive for good behavior, then what's the point, right? I mean, maybe I should just go buy my votes from somewhere and now everyone will accept my communication very happily because I have a great reputation, right? That's not what we want. So let me just summarize some of these core ideas of Sandi. There's some terminology here. the idea of the Sandi protocol is to enable senders, that's one class of communicating people, entities, to explicitly endorse communication channels with respective receivers. So that's another class of communicating parties. So we have these two classes, senders and receivers, that are in a slightly asymmetric role. What this endorsed communication channel allows them to do is that the senders and receivers can both exchange messages back and forth. They can communicate on this endorsed channel. But by being a sender, it just means that you declare to take accountability. Basically, if I'm a sender, I set up this communication channel, I say, okay, I am accountable for the appropriateness of this communication on my behalf. And the receivers can judge, right? So the receivers can say that, well, look, it looks like you are behaving really inappropriately from my perspective, and therefore I can hold you accountable for that by somehow reporting you to the reputation system. So that's the asymmetry of these roles. The receivers also can see the sender's reputation, so that could be bad, average, good, great, some sort of discrete value like this. And the receiver can, of course, use this now to make a judgment or, again, use some sort of heuristic along with this information to guess whether they should communicate or trust rather the sender. The Sandi protocol, this system, is orchestrated by a central server that we call the accountability server. And from now on, pretty much always I will just denote it by AS. The AS maintains the reputations for each sender, and it updates them, as I will explain soon. The receivers, it's very important here that the receivers do not need accounts with the AS. This was one of our key design decisions because it's very difficult to start using a system if everyone has to use it all at once, right? So it's much easier if only the senders who are the reputation subjects need accounts. Okay, to show at the high level, I'm going to go into the protocol details soon, but at the high level, the message flow looks as follows. So here's the sender, receiver, and the AS. And the goal here is that the sender sets up an endorsed channel with the receiver, and the way it happens is, roughly, the sender first requests an endorsement tag from the AS. The AS responds by giving the endorsement tag to the sender, and then the sender sends the endorsement tag to the receiver. The plus there signals that there's actually something a little bit more there, but at the high level, this is how it works. So now, by sending this endorsement tag, the sender has set up the endorsed channel. The receiver, so now some communication can happen between the sender and the receiver, and if the receiver is unhappy, they can report to the AS by simply sending this endorsement tag to the AS, and this is a report. So some very important notes here. There are no upvotes in Sandi at all, which often comes as a bit of a surprise to a lot of people, because when you think of reputation, you very often think of some more sophisticated kinds of reports. But even in GitHub stars, remember that's a unary thing. This is also unary, except GitHub stars is positive, this is a negative. So the only vote that we can have, the only vote that the receiver can submit is a downvote. There's a lot of problems with upvotes. So once you start getting into, let's add some like positive signals to this, things get really difficult because it's so hard to prevent collusion, people from upvoting each other. If you do that, you really need, if you want to prevent that sort of thing, you really need everyone to have accounts, which is something we didn't want, and you have to do some, like maybe some heuristic decisions about, okay, when do you allow people to to report. You have to understand who's friends with whom and all that. It becomes really messy. So in Sandi, really, good is sort of the lack of evil. That if you don't get a lot of downvotes, that's good. So we're really trying to measure bad behavior. The way this works now is that the AS collects these, for each sender, the AS collects these reports for some period of time, and this period of time is called an epoch. And at the end of the epoch, the AS updates the sender's score using this function called UPD, which we call a score function. So you see here the new score, SC, is computed from using UPD from the old score, and X here, like I said, SC is the score, which is a real number from -infinity to some upper bound M. This is not the same as the reputation concept that I mentioned earlier. I'm going to come to that in just a moment. The X here is the number of reports that are received for this sender in this epoch by the end of the epoch. I said that there are no upvotes in Sandi, so it's a very good question to ask, like, well, what happens if I use this for a year and now my reputation is like 0? Well, there are no upvotes, but this UPD is designed in a very careful way so that it increases your score if you don't get too many reports in an epoch. Okay, so what is this score versus the reputation that I mentioned, that I've been mentioning? So the score here is a real number. It's a very fine-grained reputation, you could say. But the problem with revealing this kind of score to the receivers is that it's entirely identifying. Because it's a real number, and even if it was an integer, if it has such a range like -infinity to some M, it can easily become identifying. And we don't want the sender's score or sender's reputation to identify the sender to the receiver. That would break some unlinkability guarantees that we want to have. Instead, what we show to the receiver is what we call the reputation. The reputation is just computed from the score using this function y. And the reputation is always in some relatively small, totally ordered set, right? So what happens here is that y is some order-preserving function and maps your score to the reputation. Lower score is worse. Okay, so let's try to describe this protocol. I am omitting a lot of some more complicated details that are difficult to explain here. I hope this text is not totally too small. I'll try to read it out. So here's the sender, receiver, and the AS. So what the sender does in the beginning is they sample secret key and public key for the epoch. So these are epoch ephemeral keys, ESK, EPK. The EPK is simply a base point multiplied by ESK. Think of elliptic curves. It actually samples also a signature key pair, so the verification key and signing key. And this verification key, it commits to with some hiding and blinding commitment. And it also commits to the receiver's information, some unique information like a name of the receiver. And I'll tell you a little bit later why this is important. It's quite interesting and subtle. But it has to commit to the receiver's information and this verification key. In fact, the verification key is much less important than the receiver info. It sends this public key, EPK, as well as both commitments to the AS. And this is the tag request. So the AS does something a little bit interesting, which is that it changes the base point to a random base point. So it chooses some secret S, some secret scalar S, and it changes G to S times G, and it changes EPK to S times EPK, and these are the G prime and X. This is done really only to get some unlinkability properties for the sender. So otherwise, this EPK would uniquely identify the sender for the epoch, and we don't want to do that. Now the AS creates an anonymous token request. So when we wrote the paper, we were thinking like privacy pass type anonymous tokens. To do this, it hashes a random nonce to, let's say, a curve point, and it multiplies that with the blinding factor R. And this is the anonymous token request that we denote by Q. It encrypts using some symmetric encryption scheme. It encrypts the sender's identity, so some internal GUID or some identifier for the sender. It encrypts that, and the nonce and the blinding factor, basically its internal state for the sender. It encrypts that using symmetric encryption. This is done because we don't want the AS to store a state that's proportional to the number of outstanding tags. So basically, we want to include this information along with the tag, because otherwise, what if I issue like 100 million tags? Now I have to keep a state that's that big with the AS. I don't want to do that. And finally, the AS signs the commitments. It actually also signs a timestamp, but I'm not really going to go into explaining what the purpose of that is. It signs the sender's reputation and the ciphertext and all this other stuff, and it sends that to the sender. And this is the endorsement tag. So the red text basically just lists exactly what I said. The sender verifies everything. It verifies the signature. It checks that the timestamp is not too far from its own local time. It verifies that this X is correctly computed from G prime. And it issues an anonymous token by multiplying this token request queue with the secret ESK. And the anonymous token is this R. Well, so far it's like a blinded anonymous token because it still has that blinding factor R in front of it that the AS put in. It also creates a proof, a very simple discrete log equivalence proof that this R is correctly computed. Okay, so it sends most of this stuff to the receiver. It sends the endorsement tag, whatever it got from the AS. So remember, this includes, for example, the sender's reputation. It sends the openings to the commitments, so that's important. That's new. The receiver needs to be able to open the commitment to the receiver's info. It needs to verify that, okay, this tag is really for me. It's very important. It needs to check that it can get the verification key. And once the receiver has received this verification key, the way it's going to be used here is that the sender can sign communication on this endorsed channel by this corresponding signing key. And that's how basically the endorsed channel is recognized. Yeah. And it sends the anonymous token request response R that was computed here. The receiver verifies everything, and yeah, it stores this verification key. Okay, so now a receiver is unhappy for whatever reason. It wants to report. So what does it do? It sends the endorsement tag. So exactly this information that it got from the AS, that the sender got from the AS. So that whole package, along with the anonymous token request response R that was computed by the sender, and the proof Z. And finally, the AS again verifies everything. Always verify everything, obviously. Now the AS can also recover its internal state for the sender by using the symmetric encryption scheme, decryption. It can then unblind the anonymous token request response, basically actually obtaining the final anonymous token. So this is this n sigma pair. And the point here is that what has happened in this interaction is that the sender has issued an anonymous token to the AES, but it wasn't directly given to the AES, because instead the sender just sent the sort of issued token to the receiver. And now if the AES has received and is able to show that, okay, I have a valid anonymous token, then that means that the receiver must have reported. So that's why these tokens can now be used as evidence of received reports. So therefore, at the end of the epoch, the AES collects all these reports that they have, organizes them by the sender's identity. And something I haven't really mentioned yet is that we use differential privacy to obtain some privacy guarantees for the reporting receiver. So what this AES does is it actually drops a random number of reports before doing anything else. And this achieves some DP guarantee. Then it uses the X, this is the number of reports, to compute an update to the sender score using this score function UPD. Again, I will talk more about that. It computes the new reputation. So the UPD and Y are totally public functions. There's nothing secret about them. As soon as anyone knows what the number of reports and the scores are, then they can compute the new values. It puts together the set of reports and it sends all of this stuff, the set of reports as well as the new reputation and the new score. I guess it doesn't even need to send these necessarily, because the sender can simply compute those by itself and verify that, okay, well, the proofs of reports are valid, so all these anonymous tokens are valid. All the different nonces are unique, so these really are different, distinct tokens. And it just has to accept that, okay, this is my new score, my new reputation. So it's a little bit of an slide of everything here. So when the receiver has received one of these tags from the sender, then we say that they have an endorsed channel between them. And I already mentioned that this verification key or the signing key that the sender had can be used to sign the traffic on that. Now, the channel doesn't last infinitely long. It lasts for some time. And basically, the tag is valid for some time, and that's how long the channel exists. This could be a few epochs. It could be, it's a system parameter. It really depends on the specific application. The receiver can report the sender at any point during the validity time of the tag. And when the tag becomes invalid, so it's out of time scope, the channel can be renewed simply by the sender getting and sending a new endorsement tag. If one wants bidirectional accountability, then just repeat the whole process in the other direction. These validity times are actually quite a complicated topic and pretty subtle topic, because there are problems like a sender might send you the tag really late so that you have no time to report. So we want to somehow prevent that kind of bad behavior. There's a lot of subtlety there, which is going to be entirely ignored in this talk. Okay, so I already said that there's something really interesting about this committing to the receiver's identity. So somehow when the sender sends the endorsement tag has to be specifically marked as being for that receiver. So why is that so important? To understand this, one has to really think back a little bit, like, what is the purpose? What are we trying to do again here? So we're hoping to provide benefit to both the senders and the receivers. So the senders are supposed to benefit because the receivers if the receivers see that, okay, this is communication on an endorsed channel, the sender has really staked something in this, the receiver is more likely to pay attention, especially if the sender has good reputation. So that's how the sender benefits. The receiver benefits because they can, of course, more easily weed out bad stuff. They can see, okay, automatically put everything that's from a low reputed sender, put it in some bin, and also maybe communication from people who are not endorsing the channels at all, maybe put it in some other bin and so on. So you can really imagine that the receiver can lessen its workload in parsing communication. Now, all of this really relies on the fact that the receiver is empowered to somehow impact the sender's reputation in a way that's proportional to the number of channels it has with the sender. It's quite, I would say, subtle in a sense. So the receiver somehow has to be empowered here. Now, if there is no commitment to the receiver's identity, what happens is that the sender could just use the same tag for any number of receivers. It just gets one tag and sends that one tag to everyone. Now, what's the problem with that? Well, what can be done with that tag? So there's two options. Either that tag can be reported only once or some limited number of times. But then the problem is that now, what if the say each tag can be reported only once, which is actually the case in Sandi, by the way. Now, I get just one tag and I send it to 100,000 people. Now only one of those people can use it to report. So that means that the receiver's relative impact on the sender's reputation is very low. It's actually like arbitrarily small because there's no limit to how many people I send it to. And therefore, actually, I am not empowered. As a receiver, I'm not empowered. Therefore, I should have no reason to trust this sender. And the sender has like unbounded benefit. Now, on the other hand, we could say, well, what if the tag could be reportable infinitely many times? Well, then what happens is that sender is essentially staking all of its reputation because there's no way to control who gets it, right? So anyone can report. Again, to fix these problems, maybe you could do something like receivers having accounts as well, which is what we don't want. So this is why it's really important to say that, okay, this tag is for you. And when your client, your email client or something receives it, it checks that, okay, this is really for you. If it is for you, then promote that email. Then say, okay, this is an endorsed email for you. Otherwise, it's not. And this is why Sandi can't work in things like settings where you have some unspecified number of receivers, like social media posts or mailing lists where you don't know who's going to get it. The security of privacy guarantees are, of course, sort of first and foremost consideration for us. What we really, well, we have 4 different kinds of guarantees here. And the score integrity guarantee says that the AS can't somehow manipulate the reports to artificially make the senders look worse. So they can't, the AS can't somehow like come up with fake reports. So each report that it receives is really coming from a receiver who received it, and the sender is in control of who are the receivers. Communication privacy means that, well, the AS doesn't learn anything about what the sender and the receiver communicate. Their communication is completely outside this system. Although AS does learn when a report is made. If you assume something like anonymous routing, then the AS wouldn't know who sent the report. If you don't have anonymous routing, then the AS might know who sent the report, and therefore the AS might learn that this sender communicates with this receiver. Reporter privacy is very important. This is simply that senders do not learn if any particular receiver reported them. So keep in mind that this has to work in cases like where the sender really maybe sends only one email to one person. Like all they do is send one thing, and they really try to probe this somehow. In none of these cases, because of a differential privacy guarantee, the sender learns, sender doesn't learn this information. Of course, as with DP always, eventually the privacy degrades if you repeat this experiment, so we do have to do some composition theorems and so on. We use a negative shifted DP distribution, negative shifted Gaussian, so entirely in the negative real number region, in fact, because otherwise we would somehow have to create valid noise tags, right? Because somehow, otherwise the AS would have to be able to say, oh, this is like the positive noise, but where did those tags come from, right? It's much easier to drop tags that it has received as reports. Finally, unlinkability just means that the sender or the receiver won't be able to, basically that the tags don't somehow link the sender, right? Of course, the sender's messages, their email addresses, or whatever other communication handles might link, but at least the tags don't. So that means that you really can use the same score across all different communication systems that you use. Okay, getting to the kind of the last topic here. This is the what we call optimality. So this is about in the very beginning I said that we have to be careful about what behavior the system incentivizes. And I already talked about the UPD function and this. I didn't really say what UPD is. So one should ask, how exactly should the updated score be computed? If the score is too sensitive, then basically the senders are not incentivized to use the system at all. Like what if I get a random report? Someone just accidentally clicks report, right? And now, well, my reputation is bad. Obviously, not a good case, and the senders wouldn't be incentivized to use it. If the score or reputation is not sensitive enough, then the senders don't care. So we need to somehow carefully craft this to get some kind of guarantee, a provable guarantee in some sense, that the optimal behavior, that's why it's called optimality, the optimal behavior for rational senders is to behave mostly well. And again, it's mostly well, not get too many reports, because you can always get some reports. There's always some random reports that you might receive. We can't make statements like, oh, don't get any. Right, so the score function, UPD, we define rather indirectly as follows. We say that, we denote by D this domain for the score. So it's what the score values can be. K here is a positive integer, and it's a sort of benefit of the doubt parameter, which you will soon see what it means. And D here is some real number between 0 and 1, not 0. It measures how much one report impacts the score, roughly. So now a function UPD from D, from the old score, cross Z, Z being the number of reports you have, mapping to the score domain again, is a score function if it satisfies the following properties. And I'm just gonna, I have a clear text version of these guarantees here because it's a little, you kind of have to stop to think about what it means. But the first guarantee is that a report is no worse than D units lower score. So D was here this real number. Second guarantee, second property or requirement is that basically more reports is bad, or less reports is not worse. The third guarantee is where this K comes in. So this is saying that after I get K reports, then each of the reports costs me at least D units of score. So this is how the benefit of the doubt enters the picture, and it's even more clear with the last property, which says that if you get K or fewer reports in an epoch, then your score doesn't go down. That's why it's the benefit of the doubt. Yeah?
Does that mean that, so if I'm a bad guy, I can, a very low volume bad guy can get away with anything, and you can't
Correct.
distinguish
That's
that
correct.
from a very high volume, pretty good guy, but who has some big bad reports. Is that true?
That's totally true.
Is that-
So there's a lot of So basically, these core functions, these parameters here, can be set per sender. So if you're a sender who sends a lot of stuff, your parameters, this K would have to be proportional somehow to how much you send, right?
How would that get set? Like who is that something the AS sets or like?
The AS would have to set it, yeah.
Is that visible in the tag or something like that? Like do you get like this is a
Good question. It's not, but it could be. Well, it's clear because the update function is sort of public. I mean, at least to the send. There's no problem in revealing it. Yeah.
Does that mean I can like improve my K value by sending a bunch of messages to my friends to like increase my total volume?
So you might, right? So there, indeed, like how to calibrate the system is a very good question. It's a difficult question. It's not clear, especially if we talk about just ordinary people, like consumers. Like I don't know how you would just tell them. Maybe you would just say that everyone has the same parameters, and it's not perfect. If you're talking about companies, so you could imagine like a sales department or customer service department would have maybe different scores in some companies. Maybe you have some more visibility in these kinds of cases, and the AES would perhaps work somehow closer with the company to enable this kind of functionality. Uh-huh.
So this also sort of strongly relies on being able to detect symbols or something like that. Because if I can generate an unlimited number of accounts,
This
then I
strongly
can-
relies on some level of Sybil resistance, right? So it doesn't necessarily mean that you can't create any Sybils, but it's not like there's any immediate break in any security or something, but it's just that the guarantees get weaker.
multiplied by that K, I guess.
Yeah.
Something like that.
I think it makes a lot of sense for us to just assume that the sender, when they just register to the AS, can or be asked to provide some identity information because there is no privacy problem to the AS during the registration. They have to, they can reveal their identities. They can say, I'm going to use this many different email addresses and etc. There is no problem with the overall system in terms of privacy of the sender.
I guess I'm thinking if you're thinking of it for consumers, like the identity problem is not a super easy one.
No, it's not easy, but I mean there are like LinkedIn is a good example where you can prove your identity using, I think, their partnership with Clear. That's one example. So I mean, clearly it can be done.
Would people do that? Is of
Would
course
people do that
different.
is a different question, right? But I mean, there's all kinds of techniques for mitigating. I think already the just SMS-based verification is pretty reasonable and has some return on investment. So, well, obviously this definition is not constructive. So here's the construction. One such, maybe the simplest that we could come up with. Basically, it's a three-pronged function. The first branch here states that the score decreases linearly in the number of reports if you have at least K reports. The second one is, these last two are recovery. So the second one says that the score recovers with this constant B. So B is some number between 0 and D, like basically 0 and 1. It recovers by this constant if you don't get too many reports, so X is less than K, and your score is bigger than some threshold. And the final branch is that the score recovers basically as fast as it went down if your reputation is very low and you don't get too many reports. In the full paper, we show pretty broad generalization of this example that allows really any number of these recovery branches. So the problem with this particular example is that the recovery is very restricted. It's not very flexible. In many cases, there's all kinds of reasons why you would want to make it so that the recovery rate is different when you are in different score ranges, for example. And this doesn't really allow that. So the generalization that we have, it really allows even up to like infinitely many different branches for this. And more flexible kind of recovery. Yeah.
Where should I think of the score starting for a new?
Starting?
For a new
It can start from any value. So usually, I was always thinking that the score starts from the perfect because you haven't done anything bad, and the whole system measures bad behavior. So it doesn't. So somehow that's most natural in my mind.
I wonder if you mitigate some of the simple risks, that if you start like in the middle, right?
Yes.
So then you have to be
Yes.
around for a certain amount of time to get
I mean, it is-
optimal scores.
Exactly. So there's all kinds of ways like that, and if we also play with the recovery rates a little bit, we can make it so that if your score is very high, it recovers really slowly. So you can do things like that and make it so that it just becomes really costly to create Sybil accounts that are meaningfully high reputed. Well, I'm not sure if I have really time to finish this optimality, so let's just see how it goes. Okay, so how do we analyze this sort of situation? The sender state at any time is a tuple. It's a sender score, X, which is the number of reports it has so far gotten in this epoch. E, which is how many epochs it still will be in the game. At some point, it will stop being in the game, right? R is a bit of an oddity. This is a bound on the total number of reports that the AS allows this sender to get during the entire span of the game. So this could be some very large number, but basically it's saying that, look, you just can't get like an unlimited number of reports. That would mean some really bad behavior is going on. And in a sense, this is needed because you have to have some sort of bound. Otherwise, as soon as the sender has some positive expectation of some sort of reward from sending stuff, even if their reputation is bad, if they can send arbitrarily much stuff, they can have an arbitrarily high total reward, expected reward. So this is such a limit. S here is a really confusing one. This is what we call the script space. So this is a set of scripts which are essentially compact descriptions of the sender's strategy of how it communicates. So the name script really comes from, I was thinking of this from sales scripts that some salespeople might have. So the idea is really that it's a sort of a compact representation of what you do when the person comes with this message that they send you. And even though it doesn't really, of course, it can't know what they tell you, it can't know what exactly they send to you, you can have some heuristics there. If the customer is really aggressive, then try to maybe, I don't know, be aggressive as well, or something like this. So the script can be very detailed or it can be very rough. It can be just like, say, I'm a salesperson, I'm a sender, and I'm trying to sell either nuts or bolts. Like the script could literally be either sell bolts or sell nuts. It's a strategy for how it behaves. We don't denote this as explicitly because it does not, because the sender's actions do not influence this, an assumption. So at any point in the game, the sender can look at its state and it can decide to do two different things. It can either say that, okay, in this epoch, I'm gonna still set up a new endorsed channel with someone. I'm gonna communicate with this receiver with this script that I choose from my script space. And we assume this is instantaneous. Or it can say that I'm not gonna do anything else in this epoch. I've gotten so many reports already. I'm gonna wait until the next epoch. So now, when I'm a receiver, taking the receiver's perspective here, when the endorsed channel is established and some communication happens, I can either decide to reward the sender with some kind of benefit, right? Maybe I purchased the bolts, right? And the reward here is parameterized by S. This is the script. In reality, this reward is a random variable. The script itself is a random variable that outputs the actual kind of conversation, and there's some probability that you get some reward when you use this when you try to sell a bolt. and you are, say, polite. And this reward happens with some probability that we denote by Q. And this Q here is parameterized again by S, the script, but also Y, which is the sender's reputation, which the receiver sees. And we have similarly a report probability, P. The receiver can also choose to both reward and report, or it can choose to do neither of those. Okay, so recall here that the Y is the reputation, which was one of these discrete values. Okay, technicalities, gonna skip those. So what is a sender strategy? A sender strategy is a function that maps the sender state to its next move, so that its move is always to wait when R is 0, so this is respecting the restriction on this total number of reports. We denote SCER by, we denote this case where you have received no reports yet by just the SCER, we just drop that X. An optimal strategy is a strategy where the sender's expected total reward during its entire game is maximized. So now there's some, it's still kind of hard to get an understanding of what these strategies look like, but we call a certain kind of strategy a normalized strategy. So I'm a sender. At epoch I can either wait for the next epoch. That was one of my moves. That's index epoch index I minus 1. Or I set up endorsed channels with different receivers, communicating with each of these receivers with script S, perhaps different scripts S, that maximize this ratio here of two expectation values. And these expectation values are things that can be measured. The sender can actually measure these empirically. I continue in this way until I have received some number of reports, XI reports. After that, I wait until the next epoch. This kind of strategy is called a normalized strategy. Therefore, the normalized strategy is really captured by a sequence of integers as such, which just tell how many reports I get before I move to the next epoch. A little note, of course, the sender does not actually know if it gets a report because the report is not sent to the sender, but the sender can make a good guess. They can try to. This is, of course, a sort of a model. It's not really the entirely realistic case.
But we are also trying to make the sender as powerful as possible to come up with the best strategy to game the system.
Yeah. So theorem 1 in the paper is that for any sender state, there exists an optimal strategy. No matter what situation you're in, there's at least an optimal way to behave. And moreover, any optimal strategy is one of these normalized strategies. Theorem 2, this is a simplification because we're not doing DP, we're not doing some of the time-related stuff. But for any score function that satisfies our definition, and any order-preserving reputation function, Y, that computes a reputation from the score, and for any sender state and any normalized strategy, there's always at least as good of a normalized strategy, where these xi's are at most k, except for the very last epoch, because in the end of the game, it doesn't matter what you do. So this means that, in fact, there's always an optimal normalized strategy where these xi's are small. That means that there's always an optimal strategy where I shouldn't get more than k reports per epoch. There's been a ton of assumptions in this. I'm not going to say this stuff, but there are some assumptions on the script space. We assume that the receivers are rational in some sense, that they don't reward bad behavior, for example. These are all formalized in the paper. And I think that I do want to say that these optimal strategies are generally non-trivial particularly because the differential privacy mechanism that we use, it always drops at least one report. So that means that there's never such a situation where you shouldn't get any reports per epoch. You should at least get one report per epoch, because that's forgiven by the DP mechanism. So these strategies are always non-trivial. What happens is, in practice, I can be a sender. I can make an educated guess that I'm not getting more than K reports. Still, that doesn't mean that I'm actually hitting the optimal strategy, but I can now say that, okay, well, I'm in a bounded region close to the optimal strategy, and I can estimate how far I am from that. So I know how much I can improve. The script space, like I said already many times, it can be large or small. So I think it's really interesting to appreciate the kind of the generality of this result and the system, because really the scripts really just say what are the behaviors that I am okay taking. Like it could be really detailed, or it could be really just be polite. All I need to do here as a sender to find an optimal strategy within like my choice of this script space is to compute empirically and estimate empirically these different values, which is something that can be done. Some performance numbers, some DP numbers, these are all in the paper. And we do have an implementation as well in Rust on GitHub. So that's it. Any questions?
I think you probably said this, but I was slightly distracted on the last slide with the DP. Does it improve things at all? Like it feels like, not knowing, I don't know.
Does it improve
Like
things?
not knowing exactly what the score would be maybe would help somehow. That you can't predict exactly. If I knew I can send exactly K, reports, and that's gonna get me, and then I get away for free, then I know I should send exactly K reports every time. But if there's some randomness in there, it feels like that maybe my incentive then is to send, and few enough results that I like.
That you don't get anything.
That I don't get anything.
Yeah, sure. I mean,
So
that is taken into account. So it's a very good question. And looking at these DP parameters, you can see that if we do higher composition, the mu, which is the standard deviation, the mean for the DP distribution, which is negative shifted, is like pretty small, right? Minus 30, say, with 20 compositions of this, whatever that means in practice. But like, that means that 30 reports on average would be dropped, right? So this is not really meaningful for a normal person. Say if you send emails, it's not like you're going to have that many different endorsed channels with different people. So you're really going to lose all your signal. You can do many things here. So you can either, well, I mean, it's a totally different situation for some companies, say let's say again, a sales department of some sort that might have like thousands, because these numbers stay the same. Like these don't scale with the number of, so it makes more sense the more volume you have. On the other hand, what you can always do is you can make the epoch longer. But then maybe the meaningfulness of the signal also degrades with that.
I guess I'm wondering, like, suppose you do have enough volume that this is not like that huge. I'm wondering if the fact that there's uncertainty actually affects the strategy you should pick or something like that.
It doesn't. So it doesn't. I mean, okay. So in a sense, yes, because for the sender, so you can always bound the DP thing. In the theorem that we present, the sender does know the ASS random coins for generating the DP noise. But even if you don't, you can always bound that.
I guess I was
So it does have an impact.
If it would incentivize you to decrease your bad behavior by whatever the maximum, whatever the bound is.
It has such an impact, yeah.
You could set it.
It has such an impact, but yeah, I mean, again, in the small sender case where you just don't send that many emails and you really want to get the full composition result. I mean, actually for one composition it's not so bad, but if you really want to get very strong privacy guarantees here over a longer time when you use this system too, then you might not be in a good situation there. And but I mean, the optimality theorems hold. Of course, the theorem was not presented here in full generality. It didn't include these things. Any other questions?
I guess it would be a very nice experiment to do in real world to see how this parameter progress changes and the impact on the uncertainty for the centers in future is. But in theory, to get them in the proofs and theorems, I think very, very difficult.
I think it's fair to say that this is a concept of a solution. It's not really it's very difficult to say whether something like this could really solve the problem in practice. There are many other scenarios. So this whole thing was motivated by the communication scenario, but there are other scenarios too where this could be useful, like any sort of maybe distributed system where you might have some bad nodes and you want to detect the bad nodes, and maybe their neighbors can like say, is this bad node behaving correctly or not? Something like that. You could use this to get a robust signal of those. So there's all kinds of other possible applications. In the communication scenario, it's really hard to say because it really depends on how people behave and things like that.
Great. Let's think in